Now we're going to get a little more specific. So here we're looking at a table of values like what you're going to encounter in the units to come. And just as a heads up, in the math world, we always write these things as the first column is x and the second column is y. This would also be a second y, so we might put a little subscript on them to show that they're different y's. So here we're asked to say which of these two would we choose, and most importantly, why in these savings accounts. Well, looking just at the end value after 4 years, I would choose this one. It has the most money. That's what he wants us to say. But if we start looking carefully and looking at the pattern here, you might see that this one is actually growing by multiplication, where this is growing by addition. So long-term, account 2 is going to end up being better. But let's first build ourselves up to find that pattern. So here we're going to look at these numbers, 2, 5, 8, 11, 14, 17, and we're going to be very specific about the change that's happening. Well, from 2 to 5, that's plus 3. From 5 to 8, that's plus 3, plus 3, plus 3, plus 3. So here's the specific part. Start at 2. Then add 3 to each number to get the next number. Here, 2, 6, 18, 54, 162, 46. Looks like we're multiplying by 3 each time, which we are. 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 54, and so on and so forth. So again, start at 2. Then multiply by 3. What's that B going on there? Multiply by 3 to get the next number. So in the first list, the values grow by adding the same constant number, and this is called linear growth. So put those two together. Linear growth is addition, adding a constant. In the second list, the values grow by multiplication, or multiplying by the same constant number. This is exponential growth. So again, let's put that together. Let's make that very explicit. Exponential growth is multiplying by a constant. And what we mean by constant is we multiply by the same thing each time. We add by the same thing each time. So is exponential growth always going to result in faster growth than linear? Well, not always in the short term. So I'm going to go back to the previous page and we can look at this in the short term. Well, this one has a little bit faster growth at the beginning. Notice we're adding 60 each time. Plus 60, plus 60, plus 60, plus 60. This one, to figure out what's going on, we're really multiplying by 1.05. How did I know that? Well, I've done this problem a bunch of times. That's how I know it. So this is 1,050 because 5% of 1,000 is 50. So it turns out the next one, to get this next value, so here we did 1.05. From here to here, we're going to do 1.05. We would do 1,102.50 times 1.05. I'm sorry, I meant to do 1,050 times 1.05, and that gets us that next value, 1,102.50. So the growth, the amount in the account starts a little bit small, but then it's long term, it's going to get much larger than this one. Okay, so in a spreadsheet, we're going to look at some linear growth. So we're told this is an example of linear growth. Let's confirm it. The way to prove something is linear is, or the way to determine what the constant is subtract the next from the previous. or subtract the previous from the next. So 45 minus 35 is 10. That means we added 10 to go from here to here. And then for that next one, 55 minus 45, well, that's also 10. So we added 10 to get here, and then hopefully you can see that there as well. So what's the next value in the list? Well, that's definitely 75, right? We're adding 10 each time. So if we're going to do a verbal description of how to obtain the value in cell, add 10 to 75. If we wanted to calculate this in Excel, you might remember this from our project 1. You're going to type the equal sign. You're going to type A6. Nope, you're going to type A5 plus 10. And then you can drag that down and fill a whole list of things. So what would appear in A12? Well, what that means is we're going to go 7, 8, 9, 10, 11, 12. If we count up what's happening here, we have to add 10, 1, 2, 3, 4, 5, 6 times. So we do 85 plus 6 tens. Oh, that's 85 plus 60. So that's 145. That's what would show up in that cell. Okay, here's another example. Now this one's exponential growth. So remember, we're going to multiply by the same number each time. And our author has made this nice and easy for us. Looks like 10, but here's the way to tell. In this case, you divide the next value by the previous value. So we do 20 divided by 2. Looks like we multiplied by 10. Let's check that that pattern holds. 200 divided by 20. Yep, that's also 10. Notice those zeros cancel, and we're back to the same thing here. So we did multiply by 10, multiply by 10, multiply by 10 each time. So the next value is just going to have another 0 on it, 20,000. How do we do this? Multiply by 10. What would we type? So we do equals, we do A5, we do the asterisk symbol, which is Shift 8 on most keyboards, and we put a 10 in there, and we've got it. All right, so the same thing here. We're going to multiply by 10 6 times, same line of reasoning. I guess we should go ahead and this was 20,000. This one would be 200,000, right? That's the 6th value in there. So to get to the 12th value, we would take 200,000 and multiply by 10, and repeated multiplication is an exponent to the 6th power. Oh, it looks a little bit like scientific notation, right, from way back when. So let me put this in actual scientific notation. We'd go 1, 2, 3, 4, 5 zeros we'd add to that. 10 times 2 to the 11th is one way to write it. And both of these written in decimal notation is, add those 6 zeros, this value. Here's how I count out to figure out what this number is in words. Here's hundreds, 100,000s, 100 millions. This is 200 billion. Okay, so in the next video, we'll look at question 15, which is a very interesting question.